Good afternoon. My name is Boris Adlung. I'm working with RIGOL Technologies Europe, and today I want to give you a webinar about advanced serial analysis with our brand new 5 GHz oscilloscope and our multifunctional real-time spectrum analyzer. Here we start with the presentation. The first part is the content of the presentation. First of all, I want to speak a little bit about the characterization of serial data signal integrity. Afterwards, I want to introduce the test devices we are using here for this presentation. First is a 5 GHz oscilloscope Ds70504 and our multifunctional spectrum analyzer with the Rsa5000n series. Afterwards, I want to speak a little bit about the data capturing and evaluation of the digital signals. Then I want to focus a bit more to such kind of analysis capabilities with jitter analysis and real-time analysis, which is needed for the digital analysis. Then we want to discuss a bit more, a deeper look with the bandwidth, which is related to the rise time of a data signal and the optimization of it. Then we want to switch from the data stream to the RF carrier and speak about analysis form on the RF carrier. Last but not least, I want to speak about the data validation and bit error rate testing. In the end, we have time for some open questions. The first part starts with the characterization of serial data signal integrity. So the first part is a description of the presentation, which is evaluate the quality of the data transmission from digital to RF. Here it's quite important when we make a design to concentrate at first to the data transmission on the digital boards and see some influences on the digital side like noise behaviors or interferences, jitter behaviors, timing effects, which is related then to a negative or a more worse RF transmission in the end. Therefore, we want to focus at first to the digital part, make an focus how to capture a digital signal, how to analyze a digital signal with the tools of jitter analysis, of real-time analysis, to take a notice to some timing drift and noise behavior and amplitude noise behavior, and then also discuss some bandwidth and rise time issues. Afterwards, we want to focus with our test devices to the carrier, RF carrier analysis. For example, the frequency analysis is quite important then, and we want to focus also to the demodulation of the digital modulated RF carrier. Last but not least, we want to make the validation and do the bit error rate testing according to fulfill the specification of the device under test. For this kind of tests, we are using two kinds of test devices. The first part will be our brand new 5 GHz oscilloscope, which is built up to the new platform UltraVision 3. This one has the capabilities of jitter analysis and real-time eye test. We are using as well our multifunctional spectrum analyzer with the Rsa5000n series, which has the real-time capabilities for the frequency analysis, and then of course the vector signal analyzer for the digital demodulation and the bit error rate testing. First of all, I want to focus and give you an introduction of our oscilloscopes. We are using the Ds70504 series. Here you can see all the other scopes with the UltraVision 2 platform. For example, the MSO5000, which goes from 70 MHz to 350 MHz, and our MSO8000 series, which goes to 600 MHz and up to 2 GHz. Also, both scopes are multifunctional oscilloscopes, which contains a mixed signal oscilloscope. That means 16 digital channels and 4 analog channels. The MSO5000 is, for example, 8 giga sample oscilloscope, and the MSO8000 is a 10 giga sample oscilloscope, which has also the capability of spectrum analysis with FFT functionalities, with protocol analyzer, and with a waveform generator. The new oscilloscope, which is used for this test, is the Ds70504 series. This is a new platform based on the UltraVision 3 platform. And this has a 20 gigasample engine inside and a memory depth of 500 megapoints standard, which can be extended to a 2 gigapoints memory depth. Here you can see an overview of the platform. So RIGOL developed their own Asic chipset for their oscilloscopes. And these chipsets are part of the Ultravision 2 platform, as well as for the Ultravision 3 platform, which is more improved. Here you can see the two positions of the two Asic chips we developed in our hand. Furthermore, we developed as well a third chipset, which is visible here. And this is assembled in our brand new RF active probe PVA8000. Later on, I give also a small introduction about this probe. This probe goes up to 7 gigahertz bandwidth. Here you can see the main specification of the Ds70500. We have in principle two models. One model goes up to 3 gigahertz and the second model goes up to 5 gigahertz. The 5 gigahertz version can work with 5 gigahertz if you use it with single channel or with 2 channels. In case you activate all 4 channels, you can still measure 4 gigahertz with all 4 channels. The maximum sample rate is 20 gigasamples, and in case you're using single channel or 2 channel, in case you choose all 4 channels in parallel, the sample rate is still 10 gigasamples per second. And therefore, 4 gigahertz is easily possible to measure. We have a maximum memory depth of 2 gigapoints, and the waveform capture rate is more than 1 million waveforms per second. With this oscilloscope, it's able to record data frames up to 2 million frames. Yeah, and of course, in case you increase the memory depth, the number of frames will be reduced. But you can, for example, extend also the memory depth. In case you select a memory depth of 1 gigapoint, for example, you can record 9 frames. So in principle, it's 9 gigapoints of data you can record. Our oscilloscope is an 8-bit oscilloscope, but from digital point of view, we have the possibility to increase it with a high resolution mode, where you can choose the resolution between 9 to 16-bit, depending on the bandwidth you select. For this oscilloscope, we are using the functionalities with the real-time eye diagram and the Jitter Analysis, as well like the implemented real-time spectrum analysis, which will be also part of this presentation. This oscilloscope can be used also remotely without installing any driver. In case you're using the LAN connection, you can use, for example, the web control functionality, which is an extended version of the web control, because we have the refresh rate of 9 frames per second, which is quite fast. Furthermore, you can use the web control for debugging issues. Yeah, you can send, for example, Skippy commands and resend and get also the results from the test device. You have also the capabilities to make easily screenshots, or, for example, if you want to record a video, it's also possible with that web control for further analysis. We have implemented the test device as an FTP server. So that means you can use the IP address of the test device, put it into the Explorer, as you can see here, and then open the memory of the test device and easily drag and drop the data or the big data immediately to your PC. The next test device we are using for this for the next several tests is our multifunctional spectrum analyzer with the Rsa5000n series. For the Rsa5000n series, we have different functionalities inside. For example, the sweep-based spectrum analyzer has following specification. The display average noise level has -165 dBm normalized to 1 Hertz, or the fast noise is -108 dBm normalized to 1 Hertz with an offset of 10 kilohertz. We have the possibility to adjust the resolution bandwidth from 1 Hertz to 10 megahertz in 131 steps, or the 6 dB filter are standard inside this test device. We have here also different interfaces like HDMI, USB, LAN interface, or we can give out the IF output of the real-time engine. So that means we have also a real-time spectrum analyzer in this analyzer form, and have a bandwidth up to 40 megahertz. in case you're using the real-time spectrum analyzer and not the sweep-based spectrum analyzer, then you have additional displays, for example, the density or the spectrogram or the power versus time or the combination of the three. Furthermore, you have different trigger capabilities, like, for example, the frequency mask trigger or the power trigger, which can be used as well. We have different modes inside. For example, as I told you before, we have the normal sweep-based spectrum analyzer inside. We have also the capability to activate the real-time engine with the real-time spectrum analyzer with a real-time bandwidth up to 40 megahertz, which can be used for the whole frequency spectrum up to 6.5 gigahertz. We have the capabilities to use the test device for EMI pre-compliance tests. We have here an EMI mode inside, specific for such kind of tests. We have a vector network analyzer for S11, S21, and distance to fault parameters which can be tested. And we have a vector signal analyzer mode for tests for digital demodulation and bit error rate analysis, what we're using also for further tests in this presentation. The next part of the presentation is to take a look to the data capture and evaluation. So first of all, we're using a test signal, a PRBS signal. We give it into our digital board to test. Yeah, we want to test the test path at our digital board, and we're using, for example, with the yellow stream. Wait a second, the video is not on. Okay, the video doesn't work. Okay, anyway, we're using the PRBS signal and the clock signal to analyze the test signal. So first of all, the target is to make some looks to some crosstalk effect, to synchronization of clock and data, and to trigger and decode to see if the principle of our PRBS test signal works. Here we're using at first a kind of decoding. Yeah? So we're using here the parallel decoding for such kind of test to see if the decoding of the PRBS signal works on a good way according to our expectations. The next part is to trigger the test signal. Yeah. Here we have different trigger forms. For example, we could use an edge trigger as a simple form, yeah, to trigger to an edge, to stabilize the signal. But we could use as well as a duration trigger, yeah, in case to trigger to the longest low duration or the longest high duration for our signals to stabilize the signal form. Or we have also the capability with this oscilloscope, in case we have a known bus signal like an I2C or an RS232 as an example, then we can use also this kind of trigger to stabilize the test signal and do our screen for much better analysis. Here we could also use the events table to display and analyze several data in one table. We have also the possibility to export this kind of clock event table with all the decoded data and compare it with the data we used it for our generator to see if all the bits are generated according to our expectations and according to our generator without losing some informations. With the Ultra Vision 3 oscilloscope, we have different decoding forms inside, and of course, also the trigger formats. For example, we could decode the parallel signals, RS232, I2C, SPI, CAN, CAN-FD, LIN, FlexRay, the 1553B bus, or the I2S bus. This oscilloscope can also be used to collect a big data stream, yeah, and thanks to the very deep memory of maximum 2 gigapoints and very high sample rate of 20 giga samples per second, we have the capabilities to zoom in and have also the possibility to make a deeper analysis than of this big time stream of data. For example, it's easily possible to zoom in as a picture above and to see some kind of glitches and go deeper into the analysis of such kind of glitch effects. Furthermore, it's possible to go deeper inside and make measurements on capabilities like rise times or bandwidth effects to see if we have impedance matching, good impedance matching in our data stream. We have also the possibility to use, for example, a good jitter analysis. Here's an example what a jitter is, and we're taking here the clock signal as an example. When we take a look to the rising edge of a clock, and we see it goes very fast to the left and to the right side, then we're speaking here about jitter effects. Jitter effects are mainly unwanted, especially when they are disturbing the clock signal or the data signal on an unwanted effect. Therefore, a measurement tool would be quite important to see what kind of jitter do we have. In case we have jitter effects, which is a problem, this tool can be used to see, okay, what kind of root cause do we have which generates a jitter? Here, for example, the Ds70500 has the chance to determine what kind of jitter we have. For example, we can display the total jitter as a result, or we can display also the deterministic jitter, or we have a chance, for example, to see if the random jitter is affected. Random jitter is when, for example, a noise source will be responsible for the jitter. The deterministic jitter is, for example, when another clock signal maybe from our PCB board under development or from something else, generate an unwanted interference to the signal and generates the jitter. Yeah, or it could be also from another data signal. It's data dependent, and this could have also some effects of the duty cycle distortion or intersymbol interferences. Here you can see, for example, a kind of jitter analysis, and we're using here in our Ds70500 at first the time view, and we make the jitter analysis of the clock signal. Yeah, so we see here as a result that we have that our jitter is related to noise. We can see this with a histogram. It's a Gaussian clock with a very small clock, and the data trend is also quite small, which is visible, and the frequency of the jitter is also visible here, which is also small in amplitude and in frequency range. With the next slide, you can see that we used as a jitter source deterministic signal. And here you can see the trend graph. We see the trend graph displays the integration of the clock. For example, if we would have another clock signal, which is a +1 or -1 signal, which is the distortion. Yeah, the integration of a 1 is a rising, it's an X, yeah, or of a -1, it's in falling, so it's a -X. And you can see this in the trend graph, yeah, that we see such kind of behavior. Furthermore, the histogram underlines the constant distribution, which underlines also the root cause of a signal with a square wave. With the frequency analysis of the jitter signal, we can see that we have a 200 kilohertz square wave, which is the problem for our jitter, and therefore you have now a chance to analyze where the 200 kilohertz disturbance, unwanted disturbance, is coming from, and you can stop and find the solution at your PCB board. The next part, which is a very useful tool for the analysis, is the real-time eye analysis. So real-time eye is something where we make a kind of clock recovery of a signal. And when we stabilize and know the clock, or the oscilloscope knows the clock, then it's possible to make an overlapping of the data signal. Yeah, and the cross of the data signal is then clearly overlapped, and this is possible then with a kind of clock recovery. With our oscilloscope, you have different possibilities for the clock recovery. For example, you can add the data rate of the signal, or the oscilloscope finds the data rate by its own, makes the clock recovery based on the data rate, or you can use a PLL clock with a known frequency as a clock recovery. It's depending on the data signal, you can adjust the oscilloscope according to your needs. What we can see now here with the eye is that we have a constant overlapping of several thousands of transitions. And we can see, for example, noise effects. We can see, for example, other short-term evaluations. In case you make a switch of a power stage, you activate something else additionally at your PCB board, and have done power jump, which causes singular distortion. You can see this as well in your real-time eye, and you can combine this also with the jitter analysis with the Ds70500n. For example, what we can measure out with a real-time eye is we have the capabilities to see the jitter or drift. Here you can see this in the red box, which can be known. Furthermore, you can see the clock synchronization in case you have the clock below in another channel open. Then you can see if you have some timing effects or problems, or if the clock synchronization is quite according to your expectations. Another part is, of course, that you see if the noise behavior of the transmission. You can see this with the 0 or with the 1, and the thickness of the 0 and the 1. And you can see this also as well, how close is your eye on vertical side because of the noise. And the jitter and the drift close your eyes on the horizontal side. And this can be measured as well with the eye diagram. Furthermore, the Risetime, you can see this in the green box here, has a direct relation of the bandwidth which is used for this data transmission. Here's the green box. Here in this display, you can also see measurement of the time view, which is zoomed in. You can see also the real-time eye measurement. The real-time spectrum analyzer is used in the blue carrier to measure the frequency spectrum then of this one, and the jitter analysis is used for the histogram to see then also the histogram figure of the possible jitter effects then here. So that means the Ds70500n can be used for different tests in parallel. We can also measure out some values. For example, you have here the possibility to measure out the 0 value or the 1 value. You can measure out, for example, also the distance, the vertical distance or the horizontal distance. And you have the possibility to measure out the Q factor. And the Q factor is quite important because the Q factor has a direct link to the bit error rate of the system, with the formula you can see here. That means as higher the Q value is better is the bit error rate we expect later on with the transmission. And as lower the Q value is, means as more the eye is closed and vertical or in horizontal, as more worse is the Q value, and as more worse is the bit error rate or the risk to have more bit errors with the transmission. So therefore, the target should be, and this can also be measured with that tool to improve our noisy signal in the end. So that means we have this as a result and want to improve it. And we found a root cause of the noise figure. Then we can remeasure it again and see, okay, without the noise, our signal is now optimized. And this is in the end also what we want before the signal will go to the RF part to transmit it over the RF carrier. The next part, which needs to be discussed, is also a deeper look to the bandwidth. The bandwidth is, of course, quite important because as more bandwidth we're using, as better is, of course, the signal. The rise time is more sharp, but we have other negative effects. For example, of course, we need more bandwidth, which is clear, but we can have also some kind of overshoot effects, which can be also sometimes a problem. Furthermore, it's quite important to know what bandwidth you plan to measure, because the bandwidth and the rise time and the bandwidth on an oscilloscope are related to the formula 0.35 divided with the bandwidth. The result is the rise time of an oscilloscope. The point is, when we have our signal what we want to measure, and we want to display the adequate rise time, we should also consider the rise time of the oscilloscope. And the result we can measure will be the rise time of the signal and the rise time of the oscilloscope, and you should make a square of it with the formula you can see. We make an example. let's use a 5 GHz oscilloscope and use a signal to measure with 5 GHz as well. So the rise time is, according to the calculation, is 70 picoseconds. Yeah. So we use now the rise time of the signal to be measured, and we use the rise time of the scope. That means the formula must be used and result into a rise time of 98.99 picoseconds, which results into a bandwidth of 3.5 gigahertz. That means also for the selection of the scope, you should know that you should take an oscilloscope which has a 5 times higher bandwidth than the application you want to measure. Then you result into a minimum failure of 2% of the rise time. Here you can see in the next test with the Ds70500 oscilloscope, also zoomed in signal, you can see, for example, also the decoded form, and you can see the frequency spectrum. The frequency spectrum is now displayed with the real-time spectrum analyzer on the top and the normal FFT, which can be activated as well. And you can see the bandwidth which is required for such kind of data. So we don't need so much bandwidth, but the rise time is quite big. And here you can see another test scenario where you can use, of course, also the real-time spectrum analyzer or the normal FFT. And we improved now the rise time to a much better result. And but you can see that we need now also much more bandwidth for this kind of signal. Furthermore, it should be very clear, I described this previously in my speech, that if in the case you improve rise time of a signal, you can generate also that kind of overshoot effects, which could occur other problems than in your design. So therefore, the compromise of the rise time and overshoot should be fine then during the design to avoid such kind of defects, effects. The next part is the analysis at an RF carrier. Here, for example, we used our noisy signal, which has not an optimized rise and fall time, and modulated it with a 2FSK modulation to an RF carrier. This RF carrier is also measured with a Ds70500n with a real-time spectrum analyzer on the top. And we used also the normal standard FFT on the bottom analysis form. And you can see that the analysis form and the frequency response is not optimized according to the expectations. In the next slide, you can see an example which has no noise configuration and an optimized rise time. And you can see a very clear and wonderful 2FSK figure according to the standard norms and according to the expectations. And this can be also analyzed with a Ds70500n. Now we're using also our real-time spectrum analyzer to measure the frequency spectrum for higher frequencies. So for example, we used now the frequency spectrum, the density mode for the frequency spectrum and the spectrogram and the bottom side. And you can see in parallel, we measure the same signal then also with the oscilloscopes. The Ds70500n makes a real-time eye test and the frequency budget for the digital area, the histogram measurement. And you can also see the negative view of the frequency spectrum with such kind of signal. What we're using as well for such kind of analysis, we use now the vector signal analyzer. The vector signal analyzer can be used to demodulate digital modulated carrier. Here we have different tools. For example, we have the constellation diagram on the one side. We have the capability to demodulate the symbols. We have here also the capabilities to display the error summary, and we see also the frequency spectrum. We have also possibilities to display other views, for example, the eye diagram of the eye or of the Q, or do also the bursts analysis and time view. And here again, you can see, for example, a signal which is disturbed and not optimized. You can see the constellation diagram looks quite bad. The errors are quite bad also on the vector signal analyzer mode. And this is the result because of the problems we have on the digital side. And with the next slide, you see, for example, an analysis form with an optimized signal. So on the digital side, we optimized now the signal. We have an optimized rise time. The noise behavior is now reduced. And we can see also on the real-time spectrum analyzer in real-time mode, the frequency spectrum looks much better. And also the result in the vector signal analyzer looks also much better. Furthermore, in case we know the data signal, we have the possibility to bring this information in the vector signal analyzer. And with this known signal, it's now possible to make a bit error rate over the time to see if the bit error rate on the RF carrier is according to the specification of the device under test. With the Rsa5000n, we could do, for example, ASK, FSK demodulation, but of course we could do also other modulations form like QPSK, 16 or 32 QRM demodulation. So we have different demodulation capabilities. So I used only a 2 FSK signal as an example during this presentation. The next part is the connection to the digital board for the tests. And herefore we have our new probe, our new 7 gigahertz active probe for such kind of tests. The video does not work. Anyway, I will go on. With that one, we have the capability, for example, we have different probe heads inside. Yeah? So for example, when you decide for such kind of probe, you have probe heads for the differential testing, you have probe heads for the single-ended testing. And for the single-ended connection, you have also 3 different kinds of hot pins and 3 different kinds of ground connection capabilities. You can replace this by your own, and the box with the replacement pins are available in this probe set. And we have as well probe heads for soldering. Yeah, so that means you can use them to solder it to your PCB board. Yeah, and you have a probe head for the differential one, which can be soldered, and you have a probe head for the single-ended, which can be used for the soldering. And the probe head you can see here on the picture, it has an automatic knob to set automatically the distance. And with the button 1, 2, 3, you can store in the internal memory 3 different kinds of distance, which coming quite often. And so you don't need to adjust everything in the beginning. You can store them, and then you can select 1 for one distance, 2 for another distance, and 3 for the third distance. And you have also the possibility to activate the light at the front tip, yeah, to have more view at your PCB board. Here you can see in the next slide measurement. Okay, to be honest, the BNC cabling is not the best for 5 gigahertz signal, but I think the result is quite clear. I used 5 BNC cabling for a 5 gigahertz signal, and we used also the probe. Yeah? And with the probe, you can see that it was the result to measure the rise time are quite good. But you should be quite carefully with such kind of tests. Because if you measure the rise time, you should aware that the rise time of the scope, the rise time of the signal, and the rise time of the probe will be part of the result you display on the screen. Here you can see some more information at our webpage. For example, we have an RF Basics test book in case you need basic information, also for pre-compliance analysis. We providing furthermore vector network analyzer application notes. We have application notes and a lot of videos for basic of oscilloscopes, and we have an application note for complex demodulation you can find at our web pages. Last but not least, most important, of course, we're providing several valid promotions currently. For example, for our UltraVision 2 solutions like the MSO8000, the 2 gigahertz oscilloscope, we have lower prices at the moment until end of June, or we're providing a free of charge option bundle which is the real-time eye, and the jitter analysis is also part of the option bundle. You get it for free currently in the current running promotion. For more information, you will find it at our webpage rigol.eu, or you can contact in UK our local UK partner Lambda Photo Matrix Ltd with the web address you can see here. Thank you for listening. Unfortunately, all my videos doesn't work with this presentation, else you would see a wonderful video of the oscilloscope Ds70504. But now you must believe me that this video is very nice. You can see also my contact address in case you have any questions. You can see the contact address from our UK distributor Lambda Photometrics, Mr. Peter Davenport, really nice gentleman. You can see also his phone number and email address here in case you have any questions or you want to request a quotation or more information about our test equipment. So please feel free to contact us. In case you have any questions, then please feel free and ask. Thank you for listening.